Okay, we're gonna pick up where we left off in lecture. So we got to the combined gas law, and as I mentioned at the end of the lecture, that's really a good one to know because again, as we talked about, pretty much as we saw from that particular gas law, you can pretty much get any of the other gas laws that you need. Again, all you have to do is basically just scratch out what's not given to you, what's told is held constant, and you really will be left with really the right gas law to use. So if you invest sort of your time into remembering this and also the ideal gas law, like I said before, pretty much you'll have any gas law that you would actually need along the way. So let's take a look at an example here of that combined gas law and make sure we can actually calculate it. Consider a sample of oxygen gas at 27 degrees Celsius, 9.55 liters, and 2.97 atmospheres. If the pressure changes to 8.25 and we heat it up to 125, what is the new volume? So take a few moments there and calculate it out. Okay, so once again, as we've been talking about, really good thing to do is just pull out the information. So obviously here we have a temperature that's 27 degrees Celsius. We have a volume that kind of goes with it of 9.55 liters and a pressure of 2.97 atmospheres. We actually have another pressure here of 8.25 and a temperature of 125. And we are looking for a volume. So we have a lot of choices in terms of gas laws, but obviously here we got a couple of P's, a couple of V's, a couple of T's. So that should direct you towards, again, the combined gas law. And as I mentioned before, it really doesn't matter sort of which ones you call ones or twos, but usually people will just kind of go based on how it is in the problem. So I'll just call all those first ones the ones and the second ones the twos here. Um, in terms of units, both pressures are in atmospheres, so we're good to go on that. Like normal here, we do need to convert our temperature into Kelvin. So we'll add our 273 to it, and that will get us my calculator. Looks like 327.15 Kelvin. Obviously, do the same thing here. I'll go this way, I think. 125 plus 273.15. Gonna get me 398.15 Kelvin. At this point, everything else is good. We are going to be solving for V2. So a reminder, as we talked about, pretty much when you go across the equal signs there, everybody's going to end up in the opposite location. So T2 is on the bottom, it will go to the top, and P2 will drop to the bottom, basically. And that means that you will end up with V2 is equal to P1 V1 T2 divided by P2 and T1 in this case. So we just want to make sure we put everybody in the right spot and we'll go P1, which is 2.97 atmospheres, V1 9.55 liters, and T2 398.15 divided by P2, which is 8.25, and our T1, which is 327.15 Kelvin. Kelvin will cancel, so will our atmospheres. That's going to leave us units of liters when it's all said and done. And we will end up with, looks like 9.55, actually times 2.97 divided by 8.25 and divided by 327.15. It looks like we will end up with a volume of 4.2 liters in this particular case. Sure. Any questions on that calculation? Yeah. Uh, That's 427 plus 273.15. That should be 300. That definitely is a bad calculator punch it. Thank you. So 300.15. That means I think this is the bad one down here. So 300.15. Give it a go again here. All right. 2.97 times 9.55 times 398.15 divided by 8.25 and 300.15. Perfect. How about 4.6 liters? Thank you. Other questions on that? All right. So again, a lot of people do have trouble rearranging this equation. So if that is a problem for you, you should take a moment to make sure you understand how to properly rearrange this equation. And also write the right numbers would help too, I imagine. All right. The next thing we're going to talk about is sort of a little bit of what we did here in this experiment, which is stoichiometry that involves gases. And stoichiometry that involves gases, it's the same as basically stoichiometry that's basic stoichiometry. So we do follow our same steps here. We take whatever they give us and convert to moles. We then will do our mole to mole relationship. And obviously before all these, we need to make sure we have our balanced equation. So balanced equation, convert to moles, mole to mole relationship, and moles to some other unit. Also, just like we did before, somewhere in this area, in case it is a limiting reagent problem we want to make sure of. So what is the main difference here with gases is really after you take your balanced equation, after you convert to moles, you do have the potential to use a ideal gas law here as step number 2. It is possible that you would use the ideal gas law there and solve for n. So that is one option. Otherwise, like normal, you could do grams to moles in a lot of cases, just like we kind of did here with the theoretical calculation. Step number 3, still the same, mole to mole. Step number 4 is very commonly where we do also use the ideal gas law. So, and I would say in a lot of cases, you may be solving for volume, kind of like what you did in this experiment, is a very common sort of place. So, in those 4 basic steps, you can use the ideal gas law at step number 2 to figure out moles in most cases. But I would say most commonly, you'll probably use it at the end of the sort of step and use it to figure out something like the volume of gas you collected, very similar to what you did in this experiment. Everything else is basically the same. So let's take a look at one here together. So let's say we have this equation here and we wanted to know what volume of CO2 would we produce at 37 degrees and 1 atmosphere if we started with 5 grams of glucose. So if we take our equation, and again, I'm just going to rewrite it a little higher so it's easier to see in here, I think. And we have 5.60 grams of it. And here, 37 degrees and 1 atmosphere. Perfect. All right, so if we take a look at this problem here, we're basically starting with 5.6 grams of C6H12O6. We want to know what is the volume here of CO2 would we produce in this case. So really in this case, we could think about the ideal gas law and the CO2, PV equals nRT. And if you think about what's given to you, we do have the temperature. We always have R, which is a constant. We do have the pressure, and we are looking for the volume. So the one thing that we're sort of missing in order to answer this question is the moles of the CO2. And that's going to really come from the stoichiometry part of the calculation. So we could use the other piece of information that was given to us and really at this point just do a basic stoichiometry problem. We have an equation that's balanced. We then want to convert to moles. So we are going to need the molar mass here of our C6H12O6. So 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens, and 6 times 16 from the periodic table for the oxygens. And that's going to give me here, hopefully, something on this calculator. 6 times 12.01 plus 12 times 1.008 plus 6 times 16. It's going to give us 180.2 grams per mole. So remember, we're going to use the molar mass here as a conversion factor. And we're going to take our 5.60 grams of C6H12O6. We're going to use the molar mass we just calculated with the grams on the bottom so they cancel to convert us into moles. And that's going to get us here 5.6 divided by 180.2, 0.03108 moles of C6H12O6. Remember that we ultimately want to get over to CO2, so we are going to do just a really stoichiometry problem here. And from the equation, we can see it's a 1 to 6 relationship. So for every 1 mole of C6H12O6, I get 6 moles of CO2. So we'll use our number from the previous step there. And this, again, using stoichiometry is what's going to allow us to go from C6H12O6, which we're not interested in, into CO2, which we are interested in. And if we do that, those guys will cancel, and we'll end up with 0.1865 moles of CO2. We now have kind of the missing piece that we need for the ideal gas law. And very commonly, here's where we're going to use it. PV equals nRT. We're going to solve for volume, which is nRT divided by P. And we're ready to kind of put everything in, except obviously, like normal, we do need to convert our temperature into Kelvin here. So again, we got to go 37 plus 273.15. And that's going to get us, this calculator doesn't like threes apparently. Let's try this again. 273.15. There you go. You can give us a 347.15 Kelvin. Now put it in our numbers, 0.1865. Remember, we always have R, 0.8206 liters atmosphere Kelvin mole. We just did our temperature there, 347.15 Kelvin. And that's all going to be divided by our pressure, which in this case is 1 atmosphere. The moles will cancel, the Kelvin will cancel, the atmospheres will cancel. That's going to leave us volume in liters. And if we do that times 0.08206, wherever it went, times 0.1865, it's going to get us a 5.31 liters, I believe, of CO2 would be collected in this case. So hopefully you can see it really is the same sort of 4 steps. But, and again, this is very common. I just kind of use the ideal gas law at the end step there to find volume. Like I said before, you could also use it on the second step to figure out moles if you needed to. Also, you should remember that you could have a limiting reagent problem as well. So you can still have a limiting reagent problem, even if it's involving gases. You can end up with it. Any questions on that one there? All right, let's try another one here. See. All right, so consider this reaction. What volume of hydrogen gas at 27 degrees and 1.25 atmospheres is required to react with 5.65 grams of phosphorus? 3097 on phosphorus, I believe. Okay, let's take a look again. It's a stoichiometry problem. So we got our equation. It's balanced. We are given 5.65 grams of our phosphorus. We want to know what volume here of hydrogen gas. And since it is a gas, we could think about our ideal gas law. We're probably going to use somewhere along the way here for hydrogen. And obviously, we are looking for the volume. We are given the temperature. We always have R. And once again, we are given the pressure. So the one thing we are missing is the moles of the hydrogen gas. So we are going to use stoichiometry here again to get to the moles of hydrogen. So we'll start with converting that into moles, the grams of phosphorus. So we have 5.65 grams of P4. We'll use the molar mass from the periodic table, which is 4 times 3097. Looks like we'll end up with 123.9 grams per mole of P4. At that point, that's going to convert us into moles. Looks like 0.04560 moles of P4. Remember, we're ultimately looking for hydrogen, so we want the mole to mole relationship between those two. And from the equation there, we can see that it is a 1:6 relationship. 1 mole of P4 gives us 6 moles of H2. That again being the coefficients that we're using. So P4 on the bottom, so it cancels. 6 moles of H2 up on top. And that's going to get us here basically that times 6. Going to do a 0.2736 moles of P4. At this point, we are pretty close to everything we need, except we'll do our conversion here, plus our 273.15 to convert it into Kelvin, 300.15 Kelvin, I hope, in this case. And now we can really do our last step, which again is our gas law step. And we're going to be converting the moles into some other unit. And here we're going to go moles to unit. And here we will be solving for the ideal gas law. And we're solving for volume by dividing the pressure to the other side. Putting in our numbers, we're going to end up with 0.2736 moles, 0.08206 liters atmosphere, Kelvin mole, and our temperature of 300.15 Kelvin, all divided by our pressure, which in this case is 1.25 atmospheres. The moles will cancel, Kelvin will cancel, atmospheres will cancel. Going to leave us liters as our unit. And in this particular case, that's going to get us 0.2736 times 0.08206 times 300.15. All right. Any questions on that there stoichiometry? All right. Let's try one last one just to finish up stoichiometry here. Let's see this one, which is essentially what we did today. Magnesium metal reacts with hydrochloric acid, as you saw. What is the volume of hydrogen gas at STP if you reacted 5 grams of magnesium with excess amounts of HCl? And again, magnesium, as you used earlier, 2431. calculation in the lab today. So in this case, we're starting with 5 grams of magnesium, and we want to know how much hydrogen gas will we produce at STP. Remember that when it does say STP, it is actually two values: temperature 273.15 Kelvin, pressure is 1 atmosphere. So again, if you think about the ideal gas law here, PV equals nRT. We again have temperature, pressure, R. We're looking for volume. So we are again going to use stoichiometry here to figure out the moles of hydrogen. So balanced equation we got. We're going to convert our grams of magnesium into moles. Divided by 2431, which is the molar mass from the periodic table. We again are going to end up with, at this point, 5 divided by 2431, 0.2057 moles of magnesium. We are then going to go from magnesium to hydrogen using stoichiometry. So it is a 1 mole to 1 mole relationship, which is a good relationship. That nothing changes. 1 mole magnesium on the bottom, 1 mole of hydrogen up on top. Again, these are going to cancel, leaving us now with 0.2057 moles of hydrogen. Now that we have that, we can use our ideal gas law for our fourth step, and we can solve for volume, which would be nRT over P. Popping in our numbers here, 0.2057 moles, 0.08206, which is our gas constant we always have. Our 273.15 Kelvin because we're at STP, divided by our 1 atmosphere because we're at STP. Atmospheres cancel, Kelvin cancel, moles cancel, leaves you liters left over. And if you do that, you will end up with about 4.61 liters. Had to switch calculators, got the right number. First off, any questions on that? As we talked about in class and as we talked about in the experiment here, we do have another option as to how we could solve this because this is at STP. Remember that only when you're at STP, 1 mole of any gas will equal 22.414 liters at STP. So this does give you that option that you could take the moles of H2, much like probably a lot of you did in the experiment today, and just use that relationship of a mole of H2 will equal 22.414 liters, and that will also give you 4.61 liters, again, without having to use the ideal gas law in this particular case. A reminder, as we talked about earlier, you can only use that conversion if you're at STP. So if you're not at STP, you can't use that conversion. You have to use the ideal gas law. But if you're at STP, you do have an option of either one you could use in this particular case. Any questions on stoichiometry involving gases? As I mentioned before, pretty much the same deal, right? Just kind of use ideal gas law usually somewhere along the way. Any questions? All right, we're going to look for today.